Okay, you've had a couple minutes to do these. Let's go ahead and work our way through them. Alright, so what'd you do with this one? The derivative of pi over 3x quantity squared. Logan?
To pi over 9 times x to the negative power 2. Wait, no, I said that wrong. Did I say it right?
That'll work, yeah. X to the negative power of 2.
It's pi,
Oh, yep, pi. Thank you. And it won't erase. We'll make it a pi. There's pi. Okay, so pi over 9 times x to the negative 2, and then what from there?
Then I put in the derivative form is equal to pi over 9 times negative 2 times x to the power of negative 3.
Okay, good. And what'll that simplify down to?
Negative 2 pi over 9 x to the power or cube.
Yeah. There we go. Negative 2 pi over 9x cubed. Okay. Any questions about that one? All right, good. Now, the next one here. H of x is 2x squared minus 3x plus 1 all over x. Right now, we don't have a really good rule for doing these. So, what do we have to do? Separate? Okay, Angel, how do we separate?
First is 2x squared minus 3x over x, and then plus 1 over x.
Okay, so you have each of these over x.
Yeah.
Okay.
And then this equal to 2x minus 3 plus x negative 1.
Yeah, that's good. You see here those first two terms have a common factor of x, so those can cancel out with the denominator, making it 2x minus 3, and then the last part there is just an x and negative 1. Good, so now we have it in a form that we can use this power rule for, okay? And then we get, that means we get h prime of x equal to what?
2 minus 1 over x squared.
Very good. 2 minus 1 over x squared. When you take the derivative of 2x is 2. The derivative of a minus 3 is 0, because that's just constant. And then the derivative here, we would bring the negative 1 out in front, and it's x to the negative 2 power. So we translate that into a negative 1 over x squared. Okay? Great job. So do we all understand this part? Is this pretty good? All right. So today what I want to look at is I want to consider some applications a little bit here. And specifically, if you look at the title of this lesson here, we're looking at applications of the derivative as rates of change. Okay? Rates of change. Now, we've been talking about the fact that we're dealing with slope. Okay? The derivative at a point, is the slope of the function at that point. And you could say it's the slope of the function or the tangent line. At that point. Okay? That's an important thing to remember. Okay? Slope, derivative of the tangent line, derivative of the function at a specific point. Now, this has to do with rates of change because, if you remember, slope is rate of change. All right? in terms of a line, it's telling us how quickly the line is increasing or decreasing as we move from left to right. Or if the slope is 0, it means it's not increasing or decreasing at all as we go from left to right. So that's what we're dealing with here, guys. And there's a number of different applications we can deal with because lots of stuff in real life has rates. Okay? Different speeds of things happening. Okay? Now, rate can have to do with motion or something like that, but it can also deal with, you know, how quickly the price is increasing as something happens, or how quickly a population might be changing. A rate can be any of a number of things. It doesn't just have to be the speed of something moving. All right. Now let's start with the most basic example of an application of derivative as a rate of change, and that is actually finding what the equation of that tangent line would be for a graph. Okay? We've talked about how a derivative gives us the slope of the tangent line. How do we know what that line would actually be? Okay? Well, if we were to sketch this, this original function, if you looked at it, I'm sure you could figure out we've got zeros at 0, at -1, and also at -2. And it says that this point 1, 6 is also on the graph. So here's 1, 1, 2, 3, 4, 5, 6. 1, 6. All right? And you guys know the basic look of a cubic. It's going to look something like this. Okay? And what we want to do is we want to find what the slope of the tangent line is at this point. Okay? Now there's a few things that we can infer even from our sketch. If we had the actual graphing calculator, we could infer a little more because we know the graph was perfect. But even from this sketch, I can tell that the slope of my line is going to be pretty steep. Okay? It's going to be positive. I can also tell that this line is going to be crossing the y-axis down in the negatives. So when I find the equation, it's going to be y equals mx minus something. Okay? Now guys, those are important things to recognize because those are the things that if you recognize them and then you make a little mistake, that's how you catch those mistakes. Okay? So I am looking for the equation of the tangent line. So a little bit of review. When we go to find the equation of a line, what do we have to know?
The y-intercept.
What?
The y-intercept.
Okay, the y-intercept we'll get eventually. We have to know the slope. And really, we can get to the y-intercept as long as we know any point on the line, right? So we got to know the slope, we got to know a point. Thankfully, we were already given the point. Okay? So there's our point. How are we going to get our slope? Find the derivative at 1. Okay? Find the derivative at 1. Now, we don't know how to find the derivative of this function as it's written, so what do we have to do?
Open the bracket.
Okay. How would we do that, Terry?
Like y equals x squared plus 3x, x cubed plus 3x squared plus 2x.
Very good. Okay. We'll multiply that out. Combine our like terms. We get x cubed plus 3x squared plus 2x. Great. Okay. And now we can find the derivative. Okay. We would need to find the derivative when x equals 1. So what would our derivative be for x cubed plus 3x squared plus 2x? 3x squared
plus 6
plus 6x
plus 2.
plus 2. Very good. Okay. 3x squared plus 6x plus 2. We're using the power rule there. Okay. So now, if x equals 1, our slope for the tangent line equals 3 times 1 squared plus 6 times 1 plus 2, which is 11. Does that match with what it looks like? We said it was going to be positive and it would probably be pretty steep, so that makes sense. Okay? Now, we have a point, we have the slope. However you like to find equations of lines at this point, go for it. Okay? You can do it however you want. You know, if you want to use point slope form, you know, y minus 6 equals 11 times x minus 1. Combine your like terms and get it in the slope-intercept form. We've got 11x minus 5. That minus 5 makes sense based on our sketch because we said it was going to be, the y-intercept would be negative. Okay? So, that's what we're looking for. Okay?
That's just point slope form.
Yeah, I just use point slope form. If you want to use slope intercept, solve for b and then plug it back in, go for it. However you guys see it. Okay, now, one thing that I want to do, the directions tell us to do this, but we need to, this is one area where we're going to learn how to use our calculators. Okay? Get your calculator out and let's learn a little bit about how to do some of this on the calculator. Okay? All right, can you guys see this here? You guys follow along. All right, so follow along as we're doing this. First thing you need to do is put those functions into your calculator. Okay? And notice here I put both the original function and I put the tangent line function in the calculator. And there they are. Okay? You can see the zeros like we said there would be at -2, -1, and 0. Okay? Now, how do we check this, okay? If I trace and I hit 1, I can see that 0.16 that we used. And if I hit, notice that's the point on the original function. If I hit the up arrow, it'll jump to the other function. And if I hit trace 1, notice it also contains the 0.16. So I know I hit the point I was aiming for. All right? I just, to get from one function to the other, I hit the up arrow, up or down arrow, and that'll switch between functions that are graphed. Nice thing with this is it color codes it. Even if it doesn't, it will say, if your calculator doesn't have color, it'll still say the equation of the function up here. Okay? But here's what I wanted to look at. This is one feature of your graph that you probably haven't used before. But remember Calc here, how we used it to find max and min points. We used it to find zeros last year. Okay? I'm going to hit second calculate. And one of those things that we didn't use, we did do intersections too. We didn't really use 6 or 7, but number 6 you should now recognize as the derivative. Okay? So we're going to come down here and we're going to use the derivative, and the way this works is I'm going to punch in an x value. Okay, it's just like trace when you wanted to find a point. Once you hit calculate derivative, you punch in an x value and hit enter, and this is really cool. Check this out. It shows you the 0.16 down here, but look at that. dy dx equals 11. Okay? Because of the iterations it does, it came up with that 1 way down the line in the decimal, but this is just 11. Okay? And what did we get our slope to equal? We got our slope to equal 11. Okay? Yes?
Would it know that it was 11 if you just had one of those, if you just had the blue?
Yes. Yes. That's a great question. Yeah, the fact that I graphed the actual tangent line has nothing to do with what I just calculated.
Otherwise it wouldn't really help you.
Yeah, exactly. So, and actually, what I can do now, I can hit second calculate, and I can do the derivative again. I could try it at like negative 1.5. What's the slope at negative 1.5? And I hit enter, and notice the point is negative 1.5 3/8, and it's approximately negative 0.25, 2.250. Okay, with three decimals. Okay, so that's really handy, especially if you needed to find the rate of change at multiple places. You can really quickly find it this way. And by the way, if you had a function that you did not know how to differentiate algebraically, you could always graph the function and figure out the derivative at a point this way. Okay, any questions? Okay. Whoa. Let's just undo that. Okay. Yeah, that's what it is. Okay. Okay, so problem number 2. We got a little bit of trig. Okay? Problem number 2 says, determine the points, if any, at which the graph of the function has a horizontal tangent line. Now, this is something we'll be using a decent amount, but if I have a horizontal tangent line, what does that tell me? The derivative equals 0, because a horizontal line has a slope which equals 0. So my dy dx at that point is going to equal 0. Okay? Okay, so basically, once you recognize that, this should tell you what you need to do. We need to take the derivative and set it equal to 0. Okay? And it asks for the points. So once we set it equal to 0 and we solve it, we can find the x coordinates of those points and then use the equation to find the y coordinates. All right? So, let's first of all go ahead and find dy dx. What is the derivative of the first part, the radical 3x? The radical 3 times x.
Take the coefficient.
Yeah, just the radical 3. That's a linear portion of the function, right? And the slope of a line is constant, so it's just that coefficient. All right, so radical 3. What's the derivative of 2 cosine x? Very good. Negative 2 sine x. The derivative of cosine, remember, is negative sine. Okay? So it's negative 2 sine x. Okay? So at this point, we set it equal to 0. I'll let you guys solve it. Okay? Take a minute here. Practice your trig and solve it. I'll solve it here where you can't see.
Problem 2.
Okay. Do we have x yet? Do we remember a unit circle? Do you guys agree with Angel? Pi over 3 and 2 pi over 3? Sine of x equaled root 3 over 2, right? So at pi over 3, sine, that's the point 1/2 root 3 over 2. Okay? So yeah, the sine is root 3 over 2. And then sine is also positive in the second quadrant. Okay? So the second quadrant with a reference angle of pi over 3 is 2 pi over 3. Okay? Again, if you struggle with the unit circle still, make sure you go back and review it. So now we just need the actual points. Okay? So if we plug in pi over 3, we'll have pi root 3 over 3 plus, what's the cosine of pi over 3? That's pi over 4. 1 over 2. Okay? 1/2. So 2 times 1/2 would be 1. And if we plug in 2 pi over 3, it's going to be 2 pi root 3 over 3. What's the cosine of 2 pi over 3? Negative 1/2. Good, because cosine is negative in the second quadrant. So 2 times negative 1/2 is the -1. Okay? You can leave your answer like that. That's the exact answer. If you plugged it into your calculator and you got a rounded answer, remember to give yourself 3 decimals. Okay? All right. Any questions?
So we plugged in x into the original equation or to the derivative equation?
Well, what are we trying to find?
The points at when it has a horizontal.
Okay, where, and those are points on what? Those points are on the function, right? Okay. And guys, actually, I'm glad Logan asked that because that's a very, very common, question to have or thing that some people accidentally do wrong. You're looking for points on the original function. So when you get those x values, you plug them back into the original function. if I forgot and I plugged them into the derivative, what would I get? 0. Remember, because that's how we got them in the first place. All right, so some people, they do this the wrong way and they wonder why all their answers come out to be 0. It's like, well, that's how you got it in the first place. But that's an easy mistake to make, so I'm glad you asked. All right, let's move on to problem 3. Okay, here's another application here. We want a coefficient of the radical function here that will make this line be tangent to the radical function. Okay? So this one's a little bit different. We have this line. We have a radical function. We don't know how much this k is going to vertically stretch it or shrink it, but we do know that the tangent line is going to be this line y equals x plus 4. Okay? We know that that radical function is going to hit 0, 0, but you know, normally it would go up like this. So obviously we can't make k equal to 1. The question is, how much do we have to stretch it? Okay? Any thoughts on how we might tackle this problem?
Just use k to get the derivative and then like equal to x plus 4 and find the k.
Okay. So you're saying find the derivative. So f prime of x. Do you guys know what f prime of x would be here?
K over 2 times negative 1 over 2.
Great, good job. That's kx to the 1/2. So 1/2 k x to the negative 1/2. Okay, we rewrote this as k x to the 1/2, and then we can use our power rule. All right. So Angel was saying, you were saying to do this. K over 2 x to the negative 1/2 equals x plus 4. What do you guys think about that? Can we solve that equation?
The line is not the derivative of the function. It's just 1 point. It's just a tangent.
That is a tangent line.
Is it just 1 point?
It's just at 1 point, yes. What? Use the point 0.04.
Isn't the slope just 1? So, and we're trying to find the slope. Like you're trying the derivative is slope, and your slope is 1. So when you set k over 2 x to the negative 1/2 equals 1.
Okay, we're getting here. We're getting here. So this is what William was saying. He said the slope here equals 1. So our derivative would have to equal 1, right?
Yeah, so it has the same slope.
But we've got a problem here, and that is we have 2 variables. When we have 2 variables, what do we need?
Get rid of 1.
To get rid of one. How do we do that? A system of equations. We got to get a second equation here. Now, this might have been kind of what Angel was thinking a little bit, but what do we know about a tangent line and the original function? They will always touch or intersect at 1 point, right? So if I set the original function equal to x plus 4. That'll give me a second equation, right? Now, how to solve this one? This isn't a system of linear equations. It's a little bit different. Let's go ahead and look at how we might solve this system. I'm going to use substitution. But does everyone, before I solve it, I should ask this, does everyone see how we got those two equations? Okay? All right. All right, so what I'm going to do with this is k over 2 root x equals 1. If I simplify the negative exponent, the negative fractional exponent, I'm going to multiply both sides by the square root of x. Because that will tell me that k over 2 equals the square root of x. Now, why would I have done that? Okay, because now this radical x right here, we can substitute out. And we can make it k times k over 2 equals k over 2 squared. Because we only have the square root of x, we need x plus 4. Okay? I had to, because this would be that, right? X is just the square root of x squared. Okay? So now we have k squared over 2 equals k squared over 4 plus 4. We've got a quadratic equation obviously here. I'm going to multiply everything by 4, so I have a 2k squared equals k squared plus 16. K squared equals 16. Which means that k is plus or minus 4. So which is it? Or is it both? Just the positive. If it were negative, then this would be going down here, and it would never touch that line. Okay?
Mr. Dixon, in one of the systems of equations, it's k over 2 radical x. How'd you get there?
I just took this negative 1/2 power, and
okay.
yeah. Okay? So this means k has to be 4. You can test it if you like. We could even test it on our graph in our equation if we wanted to plot this. Make it a 4 square root of x and make our make the line x plus 4 and make sure that they actually intersect. Okay? And only intersect at one point. Okay? That's how we could solve that. Alright, we didn't get to this very last one, but it's just another application. Same idea. We could, we'll pick up there tomorrow and finish off this last one. Okay? Alright, so let's take a quick look at our last example. We have at time t, a diver jumps from a platform diving board that's 32 feet above the water. The position of the diver is given by s of t equals negative 16t squared plus 16t minus, or plus 32, where s is measured in feet and t is measured in seconds. Okay. Now, as we're looking at this, one of the things you need to understand about this function is what distances we're talking about, what the movement is that we're talking about. Okay? What is this motion or distance that we're talking about in this situation? Okay, the diver's jumping into the water, okay? But how are we measuring, I should say, maybe that'd be a better way of asking it. How are we measuring the distance? In feet, that's our unit of measure, but how are we measuring it? What's that?
How far are you from the platform?
Okay, how far he is from the platform? Are you talking like out? Okay. All right, so let's think about that. Look at how the other distance, what other distance is given to us in the problem?
How far up?
Huh?
How far up he is?
How far up he is. He's starting 32 feet above the water. So if we're talking about that, then what is this distance probably talking about?
Height.
Probably is height, okay? And I'm glad you pick up on this, because there's two ways of seeing this. You've got the water down here, and you've got this platform that he's standing on. That's 32 feet up, okay? The distance he is away from the edge is actually not taken into account here. Now, you could model it based on that. You know, how far away from the edge of the board does he get as time goes on? But in this case, we're actually only looking at the vertical height from the water. Okay? So he jumps up and then goes down into the water. He might have jumped like this. He might have just jumped like this and barely missed the edge of the board. We don't know. Okay? But in this case, all we're looking at is that vertical height. This is what's called rectilinear motion. Or, those of you who had SL last year, this is related to what we were doing with kinematics. We're taking a situation where there might be other dimensions involved, but we're only focusing on one dimension as it relates to time. That's actually what our next lesson here is all about. Okay? So as we're looking at this, the first part is, when does the diver hit the water? And how are we figuring that out? The x-intercept, okay. Is there any calculus actually taking place here? No. All right. This is just a basic algebra problem. You're finding the x-intercepts, or the zeros, of this function. And you all know how to solve a quadratic, so I'll just do this kind of quickly here. I'm going to divide everything by -16, so I have just t squared minus t minus 2 equals 0. And then that's something I can factor, so it's t minus 2 times t plus 1, which is 0. So what are my times? 2 or -1. So we're going to use the 2, because in our realistic situation, it wasn't moving before we started looking at it. Now, there may be applications where we could consider a negative time because it was already moving when we started the clock. So t equals 0 isn't when it first started moving, but this isn't one of those times. Okay, so now we get to part B. What is the diver's velocity at impact? Now, if we're talking about velocity, what ought to come to mind? Derivative.
So, do you take the velocity at the x or at the 0? So at 2?
Yes, okay. So we found when he hit the water, so we would know the time. If s is our position, or our height, the rate of change in our height is our velocity, okay? So velocity here is going to be our position that we take the derivative of. So what is the derivative of s of t? What is it? We've got our function up there. What's the derivative? Plus, what was it? 16. Okay? Negative 32t plus 16. There's our derivative. Again, just using the power rule at this point. Okay?
How would you use the power, please?
The power rule was 2 times the negative 16 is negative 32, and now it's only t to the first. 1 times 16 is 16, and it's t to the 0, so the t's gone. And the derivative of a constant is 0. Yeah, you can do each part separately.
Okay.
Remember, we said that's derived from the fact that when you had a limit of multiple things added together, you could just take the limit of the one, then the limit of the other, then the limit of the other. Well, remember, a derivative is just a limit. It's that whole definition. The limit is delta x approaches 0. Okay, so that rule just carries right over here to derivatives. If you have a derivative of a sum, you can take the derivative of each term in that sum. Okay? Oh, of course. Of course. Okay, so how do we get our answer here? The velocity at impact? Plug in 2. There we go. When does it impact? It impacts after 2 seconds. So we have negative 32 times 2 plus 16 is a negative 48 feet per second. Okay? Now, is that kind of disconcerting to anybody that it's negative? Does that look odd?
Yes.
Okay. Why?
Actually, no.
Why not?
Because it's negative slope. Because 1 point.
It is negative slope. What were we going to say?
I was just going to say from 1 point to like bottom of it.
Okay, yeah, because we're going downward. That's why they asked for velocity as opposed to speed. Good, Angel. As opposed to speed. Velocity, remember, is a vector quantity, okay, which indicates both a magnitude and direction. The direction in this case is that negative, whether it's positive or negative. Okay, so there's our direction and magnitude. If I asked for the speed, okay, because, you know, if we were just asking, you know, how hard is he going to hit, you know, we were calculating some kind of force, it doesn't matter if he's going 48 feet per second downward or upward or sideways, ramming into something, it's going to be the same force, okay? So in that case, maybe we would just use the speed, but the speed is simply the absolute value or the magnitude of the velocity. Okay? So in this case, the speed would have just been 48 feet per second. Okay? So. All right, so that's all for that.